So when we last left off, we discussed drawing chair conformations for cyclohexane systems and identifying the lowest and highest energy conformation. So in this case, we're asked to draw both chair conformations for the following compound, and our goal is to identify the lowest energy conformation. Okay, so to start off, we're going to find a wedge substituent, and I'm going to arbitrarily label this at carbon 1. So following our shortcut, I'm going to label the configuration of each of my substituents, keeping in mind that if I have a dash substituent, it has the opposite configuration. You can also think of it as drawing the cyclohexane ring. So you can draw your cyclohexane ring. And if we have carbon number 1 right here, then this wedge substituent will be pointing up, so it'll be in the axial position. At carbon number 2, we have a hydrogen that's axial pointing down, and our T-butyl group is equatorial pointing up, respecting the fact that the T-butyl group has a wedge. So continuing on, well, let's draw out the rest of our hydrogens so we can visualize our 1,3 diaxial interactions. So at carbon number 6, we have a dashed methyl. And so our methyl group is pointing down, and it would be axial pointing down. Then we draw out our hydrogen for completeness. Okay, so let's now look at our ring flipped form for this compound, or for this, let's look at the ring flipped conformation for the following cyclohexane ring. So as we discussed for ring flips, carbon 1 is brought down, carbon 4 is brought up, and the axial and equatorial, all of the axial substituents become equatorial, and all of the equatorial substituents become axial. So after a ring flip, we're left with the following chair conformation. Okay, carbon number 1 is down here, carbon number 4 is right here, and carbon number 6 is right here. It's really important that you don't mix up your carbon numbers after a ring flip. The methyl group is still pointing up, except this time, instead of being in the axial position, it's in the equatorial position, pointing up. The T-butyl group is still pointing up. So it's axial pointing up. That's already a bad sign. Let's fill in the rest of our hydrogens for completeness. Remember that in a chair conformation, let me just adjust this a little bit. Just trying to make it a little bit easier to see what's going on here. Now at carbon number 6, our methyl group was previously axial pointing down. Now, rather than being axial pointing down, our methyl group is equatorial pointing down. Okay, so we've completed our ring flip, making sure to properly label our carbons. Now let's assess and let's identify any steric and torsional interactions. So in our first conformation that we'll label A, what steric and torsional interactions are at play? What steric and torsional interactions are at play? Would anyone like to volunteer? So we have a hydrogen methyl 1,3 diaxial interaction. Okay. And how many of these 1,3 diaxial interactions do we have? We have 4 of them. And would someone remind me, what's the value of a 1,3 methyl hydrogen diaxial interaction? How many kilojoules is that worth in terms of energy? What is the value of a methyl hydrogen 1,3 diaxial interaction? Very similar to a Gauss methyl interaction. What's the value approximately? It's about, well, 15.2 would be the when you multiply by 4. An individual interaction is 3.8 kilojoules. Yep. But in the chat, they've correctly noted the total value of all of these 1,3 diaxial interactions. Okay. Are there any other interactions at play here? Are there any other interactions that are present in this molecule that we need to note? Any other interactions that we can see? Well, immediately what stands out to me is I have bulky substituents on adjacent carbons, and they're separated by 60 degrees. They're pseudo-staggered. So we also have a methyl T-butyl Gauss interaction, which we would estimate, considering that a methyl Gauss is around 4 kilojoules, this methyl T-butyl interaction will probably be around 7 kilojoules, just order of magnitude. So adding these together, we have a total amount of strain of 22.2 kilojoules of strain for structure A. Let's look now at structure B. And this is where the T-butyl group really begins to be problematic. So, looking at structure B, what interactions do we have in structure B? What interactions do we have in structure B? What steric or torsional interactions do we have in structure B? Would anyone like to volunteer some suggestions? Do we have any diaxial interactions at play in structure B? Yep, so we have a hydrogen T-butyl 1,3 diaxial interaction. So we have a T-butyl hydrogen 1,3 diaxial interaction. And looking at our notes, what's the approximate value of a T-butyl group 1,3 diaxial interaction? Would someone like to give an estimate? Is it large or small? Is it very favorable to have this giant T-butyl group sitting in the axial position, bumping into our axial hydrogens? What's the value of this hydrogen T-butyl interaction, roughly? Would someone like to estimate what is the value of a single hydrogen T-butyl 1,3 diaxial interaction? So looking at our notes, so again, remember when I gave you this table of A values, so checking all the way at the beginning of the note set for this discussion, we see that a T-butyl group has a 1,3 diaxial strain value of 11.4. So then we'll plug in that number into our analysis. So a hydrogen T-butyl 1,3 diaxial interaction introduces about 11.4 kilojoules of strain. Since we have two of these interactions, we have a pretty large amount of strain introduced by placing this T-butyl group in the axial position. For students who are noting also in the chat, outside of these diaxial interactions, we also have a methyl-methyl gauche interaction, which costs us about 3.8 kilojoules. Additionally, and this is a little bit hard to see, but if we take a look at these two structures, we see that we also have a T-butyl methyl gauche interaction. And that in turn costs us roughly 7 kilojoules. So adding up our total amount of strain, we see that we have a total amount of strain 29.8 plus 3.8. That gives us a total amount of strain of 33.6 kilojoules. So then, for our lowest energy conformation would thus be conformation A. In general, we place bulky substituents equatorial to minimize strain. Generally, if you have a T-butyl group, the T-butyl group can be thought of almost like a lock. T-butyl substituents are almost always equatorial. It's very, very, very rare to have a T-butyl group in the axial position. Just to highlight the methyl-methyl gauche interaction, because a student asked in the chat, it would be between these two methyl groups, which are on adjacent carbons that are separated by a 60-degree dihedral angle. A typical gauche interaction. Any other questions on this example? If not, let's keep going now and let's look at conformations of cyclohexane. So In our discussion of cyclohexane, our discussion is not entirely complete. Our discussion is not entirely complete. Cyclohexane can adopt many different conformations, and the background thermal energy is sufficient for cyclohexane to undergo a ring flip and rapidly interconvert between these available conformations. Now, the reason why we focus so much on the chair conformations is that the chair conformation of cyclohexane is the lowest energy conformation. The reason for that is torsional strain is minimized and the substituents are all staggered. If we make a Newman projection of each of our substituents, we notice very clearly that those substituents are separated by a 60-degree dihedral angle. Now, what we're going to do is we're going to talk through, and I'll show with the model kit, the step-by-step process from which cyclohexane interconverts between two chair conformations. So to do that, I'd like you to get out your model kit. Okay, so I'd like you to get out your model kit and I'd like you to make a model for cyclohexane. Okay, so first and foremost, here is our typical chair conformation for cyclohexane. I put a methyl group just so that way it's clearly visible where carbon number 1 is. So does everyone see the following structure? Is everyone clear on where we're starting out? So we're starting off with our chair conformation of cyclohexane, which looks something like this. Now, the first step in our ring flip, is that we're going to take carbon number 4, the carbon that's pointing down, and we're going to bring it into the plane. This is known as the half chair conformation. This is known as the half chair conformation. And the half chair conformation looks something like this. So looking at it from a top-down perspective or in a side-on perspective, we notice something that's a little bit striking about our half chair conformation. And to help you visualize this, let's just look down one of our carbon-carbon bonds and let's see if we can pick up on the central theme of the half chair conformation. What do we notice about the half chair conformation? What do we notice about our substituents? Are they staggered or eclipsed? Looking at our substituents, looking down this carbon-carbon bond, what do we notice in the half chair conformation? Are our substituents staggered or eclipsed? Comparing these two substituents, they're eclipsed. Exactly. The half chair conformation is very high in energy. It's about 44 kilojoules per mole higher. This is the result of angle strain and eclipsing interactions. So if we were to fill in our hydrogens for this model, the immediate thing that stands out to me is the ridiculous amount of eclipsing interactions that we have. So we've essentially locked all of our hydrogens into the eclipsed conformation. And we've introduced a pretty egregious amount of torsional strain as a result. Okay, so just to summarize what we've done. So we started out with our typical chair conformation. Okay, we moved carbon number 4 up into the plane of the page. This is known as the half-chair conformation. We've moved carbon number 4 into the plane of the page, and we've introduced a fair number of eclipsing interactions. Okay. So continuing on with this process, from the half-chair conformation, we next adopt what is known as the Twistboat conformation. The Twistboat conformation, as its name implies, is designed in a way to stagger and separate what are known as these quote-unquote flagpole substituents. So let me show you the process for getting to the Twistboat conformation. So in this case, so we start off with our half-chair conformation. And then we're going to bring, so in our half-chair conformation, we're going to bring the planar carbon number 4 out of the plane of the page, and we're going to leave it pointing up. Now, rather than adopting a formal boat conformation, which looks something like this, instead, we're going to adopt the intermediate Twistboat conformation, which looks something like this. Does everyone notice and does everyone see why we use the name Twistboat? We have slightly adjusted the orientation of our carbon-carbon bonds in order to separate our flagpole substituents. Does everyone see how, as a result of this twist, as a result of this distortion in our carbon-carbon bond arrangements, we've generated some distance between our flagpole substituents, which are right here. Does everyone see how this twist can help separate our flagpole substituents? Okay. Additionally, it also minimizes torsional strain, because if we look down one of our carbon-carbon bonds once again, if we look at a Twistboat conformation, one thing that we notice that's pretty interesting is that if we look at our substituents, are our substituents staggered or eclipsed? What are they closest to? Are they fully eclipsed or are they sort of staggered? Yeah, our substituents are somewhat staggered. So these are two major benefits of the Twistboat conformation. It minimizes this steric strain while also minimizing torsional strain. So as we notice, for example, in our Twistboat conformation, our hydrogen substituents are almost pseudo-staggered, and our flagpole substituents are separated by the greatest amount of distance. Now, continuing our process of the ring flip, we go from the Twistboat conformation to what is known as the boat conformation. Now, to showcase this, so currently we have our Twistboat conformation, and to adopt the boat conformation, we're going to continue to bring our substituent up. And now, as we can already sort of tell the problem with the boat conformation, so we went from the Twistboat, which looks something like this, to the boat conformation, which looks something like this. Would someone like to volunteer and tell me a problem with the boat conformation? What do we notice in the boat conformation that's a little bit problematic? What do we see in our boat conformation? We have eclipsing interactions. Yes, that's one important thing to note. Our substituents are eclipsed. But also we have a steric interaction. And as we can notice quite clearly with our flagpole substituents, these bulky flagpole substituents are now brought in close proximity. So we have a steric interaction between quote unquote flagpole substituents. Okay, so to show everyone the step-by-step for a ring flip, let's start out. So let's start out with our chair conformation and let's walk through each of the steps to go between chair conformations. So we're starting off with this initial chair conformation. Our methyl group is axial. The first step in a ring flip, we take carbon number 4 and we bring it into the plane of the page. What do we call this conformation where we only have one carbon out of the plane of the page? What do we call this conformation? What do we call this first conformation that we've accessed? Half chair. Yep, exactly right. So we went from a chair to a half chair conformation. Now, in our next step, we're going to adjust and we're going to bring, so let me show you these steps momentarily. So we have our half chair conformation. We're going to bring carbon number 4 out of the plane of the page. And we're going to adopt a modified conformation. What do we call this modified conformation? With a small twist in its carbon-carbon bond orientation to minimize steric strain. What do we call this conformation? We've now brought carbon number 4 up. What do we call this conformation? Twistboat. Yep, exactly right. It's lower in energy than the half chair conformation because we have minimized our steric and torsional strain. Okay, continuing on now, we're next going to adopt the boat conformation, which looks something like this. So we've removed our twist. So we've adopted our boat conformation. Now, we have to bring this methyl group, down. So what we're going to do is we're going to adopt an alternative twist boat conformation. So here's our first twist boat conformation. Here's our second twist boat conformation. Does everyone notice how the two twist boat conformations are different? I'm going to label it as such. This is twist boat conformation number 2. Now, continuing on, we're going to bring carbon 1 down into the plane of the page. And we're going to form, so we're going to bring carbon number 1 down into the plane of the page. And now we have the following conformation, which is our second half chair conformation. Finally, we're going to bring carbon number 1 below the plane of the page. and that gives us the following newly adjusted chair conformation. And as everyone can see very clearly, this methyl group is now equatorial after our ring flip. So this energy diagram is drawn for only hydrogen substituents. Note that when we have non-hydrogen substituents, the energies of each of these conformations will vary. So you need to keep that in mind, that the half chair conformations and twist boat conformations may not be identical in energy. Okay, so let's show this once again. So we start off with our typical chair conformation. We bring carbon number 4 up into the plane of the page, and we make our half chair conformation. Then what we're going to do is we're going to bring carbon number 4 up and adopt a twist boat conformation, which looks something like this. Then we'll adopt the boat conformation, which looks something like this. Next, in our process of bringing our carbon number 1 down, we'll adopt our second twist boat conformation, followed by our second half chair conformation, followed by our final chair conformation after a ring flip. To showcase this in one fluid motion, so we bring our carbon number 4 up into the plane of the page. Next, we continue to bring carbon number 4 up into the plane of the page, and now above the plane of the page. We adopt our boat conformation, then our second twist boat. Then we bring carbon number 1 down and we get our half chair conformation. And then we bring carbon number 1 down an additional time and we get our final chair conformation. You should be comfortable drawing out each of these intermediate cyclohexane ring conformations. Does that make sense to everyone? Okay. So keep in mind, we can analyze the steric and torsional interactions in other cyclohexane conformations exactly as we've done for chair conformations. So let's talk about some common mistakes that are often seen when students draw a ring flip. The first mistake that I often see is they draw the ring flip cyclohexane, but they do not adjust the carbon numbers. If this is carbon 1 will end up over here after a ring flip. You can immediately tell that something is wrong with this attempted ring flip because this methyl group here is axial pointing up. So this would look something like this, wedge. Well, in this case, after a ring flip, this structure is representing the following conformation. And this really helps you see where the problem is. This really helps you see This structure is representing the following conformation. So the main issue with this mistake, and this common mistake that is often seen, is that after a ring flip, our methyl is still axial. This structure is equivalent to the following conformation. And we can clearly tell that if we compare these two compounds, and we compare these two conformations, these two conformations are okay. So let's discuss this. So first, we start off with an axial methyl pointing up. After a ring flip, the methyl is still drawn axial. That's problematic, not only because, for example, in this case, if this is carbon 1 here, carbon 1's brought down, carbon 4 is brought up, you've ended up moving your methyl group to carbon number 2 arbitrarily. So if we wanted to showcase what this structure would look like after a ring flip, just to demonstrate this completely, after a ring flip, this would be equivalent to the following structure. And as we can tell, these two structures are clearly different. These two structures are clearly different. So make sure after a ring flip, you make sure to reverse the axial and equatorial positions of your substituents. Additionally, make sure your carbons are appropriately adjusted and that you keep your substituents attached to the correct carbon number. So here's another example that highlights this carbon numbering issue. So in this case, this methyl group's at carbon 1. After a ring flip, carbon 1 ends up at this substituent, and our methyl group has now moved to carbon 2. This may not seem like a big deal, but keep in mind our methyl group is axial up in this first case. So it has a wedge. In this second structure, our methyl group is equatorial pointing down. So remember, ring flips do not actually alter the stereochemistry of any of our substituents. They don't alter the relative three-dimensional arrangement of our substituents. So our methyl group should be up in both of these chair conformations, both before and after a ring flip. In general, ring flips, and this is always true, ring flips do not convert up groups to down groups. You do not invert your stereochemistry during a ring flip. So for example, in this case, we have an axial up substituent, and it would not be correct to draw this methyl group as axial down after a ring flip. Instead, the correct ring flipped cyclohexane conformation will look something like this, where our methyl group is in the equatorial up position. Does that make sense to everyone? These common mistakes that are often encountered, does everyone see the issue with these mistakes? we're talking about them because I see them a lot on exams and want to make sure everyone's aware to avoid them in your discussions and in your drawings of different chair conformations. Okay, so let's keep going now. And let's discuss the conformations of polycyclic molecules. So, the most obvious extension of our analysis of cyclohexane systems would be to look at the decalin system, which consists of two cyclohexane rings joined to share two carbon atoms. These are known as bridgehead carbons, carbon 1 and 6. So these two carbons are known as bridgehead carbons. Now, there are two isomers of decalin, trans or cis. In cis decalin, the hydrogen atoms at the bridgehead carbon are on the same face of the rings. So, for example, in this case, this hydrogen can be thought of as quote unquote axial up, while this hydrogen can be considered equatorial up. Both of these hydrogens have a wedge. In transdecalin, the bridgehead hydrogens are on opposite faces. So we have a hydrogen that is axial up and a hydrogen that is axial down. Now, this is really important because it directly limits the amount of conformational flexibility that we have. So if we make a model of cis and trans decalin, we notice some pretty interesting things when it comes to their amount of conformational flexibility. So allow me one moment to put together a small model of cis and trans decalin, as it's really vital for our follow-up discussion. So cis decalin, both of our hydrogens are on the same face. Trans decalin, both of our hydrogens are on opposite faces. Okay. Let's look at, just like any cyclohexane system, cis and trans decalin can and will undergo ring flips. So let's look at how cis and trans decalin undergo changes in conformation as they undergo a ring flip. So both compounds can be represented using chair cyclohexane conformations, and flips and rotations do not interconvert these cis and trans stereoisomers. One thing that's unique is that trans decalin cannot ring flip. And this is driven by geometric constraints. This is driven by geometric constraints. So, the following is the structure for trans decalin, and as we try to undergo a ring flip, one thing that we immediately notice is that because these hydrogens, because our two decalin hydrogens are locked trans to each other, there is no way for us to flip the ring. It's geometrically forbidden. There's no way for us to flip these axial hydrogens into the equatorial position without introducing an egregious amount of angular or bond strain. So as you notice, no matter how hard I try to initiate a ring flip, it doesn't work. I'd break my model kit if I kept going. If we look at cis decalin, however, cis decalin is much more conformationally flexible due to the relative arrangement of the hydrogen and ring substituents. And as we see for cis-decalin, where we have both of our hydrogens, where we have both of our hydrogens in the give me one moment just to put together the cis-decalin structure and get it set up in the right conformation for you to visualize this. So because cis-decalin has a greater amount of conformational flexibility, it can readily undergo a ring flip. And it's geometrically permitted due to the relative position of our two hydrogen substituents. So we won't ask you to do detailed conformational analysis of decalin systems. I just wanted to bring it up as an extension because essentially when decalin undergoes a ring flip, we in turn end up flipping both of our cyclohexane rings. So it's just like we're doing two cyclohexane chair conformation ring flips at once. Any questions on cis and trans decalin? Cis decalin is conformationally flexible enough to undergo a ring flip. Trans decalin, due to the relative position of the hydrogen substituents, is geometrically unable to undergo a ring flip without introducing a pretty large amount of angular and bond strain. Any other questions on this example and this chapter? So this is the last example for chapter 4, and we're going to get ready and we're going to move on and start discussing chapter 5, which focuses extensively on stereochemistry and stereochemical analysis. Does this make sense so far to everyone? Okay, so we're going to switch gears now.